So we're going to do two things today together. And the first thing is to create a porous media in 2 dimensions, as well as then use periodic boundary condition to impose loading on the structure and then extract the result to see what kind of stress strain data we're going to see. Please do watch to the end because we're going to look at the effect of porosity on the effective properties of a homogeneous material. Let's sit back and relax as we get started with this video. Look at the result that we generate. It will be something like that looks like this, and in the end you could see how the porosity is redistributing the stress history in the material. The interesting thing here is that I've used periodic boundary condition in order to model this problem, and though this is exactly what I want to show you in this modeling. So let's go into how we can actually do this. So the first challenge here is how on earth do you actually create this porous media, especially the fact that you've got the geometry and then you've got also a random distribution of particles within the domain. One could go ahead and do them manually one after the other and create all these different holes individually and make sure that they are not intersecting and all that. But I've got a software that I developed called MultiCalGen, which we're going to use to sort of to do this. And basically, if you want to get a hold of that software, please look in the description section of this video where I put a link of how you can get hold of it. It's a MATLAB based software, and essentially when you get hold of it, it will appear with 2 files like this, one which is the executable that does all the heavy lifting, and then the second one here. So if I drag this into this window, this is in MATLAB, then basically it's a computational options control deck file, so it helps you set up the job in the way you want to do it. So this simulation that we want to do, we want to set up a porous media with a length of 100 microns and a width of 100 microns. This is in 2 dimensions. The diameter that we want to work with is something quite small, about 5 microns diameter in this system. And the volume fraction we're going to work with here is probably a volume fraction of, let's say, 20%. So the 20% of this porous media is essentially made of voids, and then we can leave all the other bits. So if you get hold of this software, there is a documentation file that comes with it that helps you understand all the meaning of all these parameters. But for now, this top end is really all that we need. And so once you finish setting this up, what we need to do is right click here and run the model. So what it will do is it will automatically go ahead and create the porous media or create the virtual domain for you, and this is sort of the result that you're going to get. So if you just study it a little bit, so we've got 104 circular inclusions, which in this case is the porous voids, the diameter is 5 microns, like we said at the beginning. The size is 100 by 100, and it's got a volume fraction of 20%. So essentially it looks okay, and we're happy with that. But this is a MATLAB. We really need this to get into ABAQUS. So we're going to close this file and go back to the workbench within ABAQUS where this job is being set up. And then you can see that there is a folder created here. So if you open that folder, you get some extra information. So the data that we have just shown, the graphs and all that, and some even the coordinate systems of those inclusions. So the essence of this is that you can go ahead and use this coordinate system to manually bring them into ABAQUS and set it up. But I didn't want students to do that. So there is this ABAQUS simulation folder, which essentially, if you open it as text within here, is essentially a Python script. And so MultiCalGen has created this Python script that helps you create everything that we need. So essentially, what we're seeing visually, using this MATLAB graphical input, can also be translated directly to ABAQUS by simply running this script. Please, if this is the kind of content that you like and you want to learn a little bit more around periodic boundary condition, represents volume element modeling, or the general issues around computational modeling, I make this sort of videos, and I do encourage you to subscribe so that when contents like this are made, you'll be the first to see it. And also, if you have ideas of videos you want me to make, please do put them in the comment section of this video. I do look at all the comments, and I do try to respond to all the comments, and where possible I also try and make videos as student request. So please do go ahead and subscribe to this channel so that the community, the CMEDN community that I'm creating, will continue to go. So what we're going to do is I'm going to copy the link where this particular file is, this particular Python script is, and then I'll go back to this system. Okay, so what we're going to do, I'm just going to rename this and say, okay, this is probably number 2. All right, so then we're going to basically set up the job. So we already have it here. So I'm going to then do file run script, and then I'll paste the link where this file is, and then I basically run that Python script. And instantly we can see that it created a Python script for us. It created the model the way we wanted it, and we can see this is number 1. So we have the file, and it's basically set up here. But at the moment, it's not looking as if it's a void in the way we want it to be. So because MultiCloudGen is set up to really create composites, by default, so we're going to do some adaptation on this. So we're going to delete that particular model, leaving only the voids that we want, and then we'll go to the assembly module. Within the assembly environment, I'm going to also resume these two. So I'm going to resume them, and then we delete that particular one. So basically what we see here is essentially the model set up in its classic form, with the voids in the classic sense. So we're going to then create a voidage from them. So what do we need to do? So we go to the assembly module and click on this button that says merge cut. So I'm going to then call it my porous RVE, something like that, in 2D. Now with that information, I want to do a cut. My merging is by cutting the geometry, and I'll select all that. So what it says here is select the instance you want to cut. So we select that instance and basically select the instance that you want to use to cut it. So I'll select everything here, which would only select the instance remaining. Obviously, we've already picked on the first one and then clicked on. So instantly now we have our porous media. So what I'm going to then do here is I'm just going to import a few things, that we already done before into this model. So if we do model, I'm going to copy objects from, we're copying from model 2, the one that I've already done before, and we're copying into model 1, which is the one we're working with. So the instances are basically the things we need to look out for. So we're going to look out for the instances of the fiber and the matrix. So we're going to copy the E class and the polypropylene, which is so essentially the polypropylene is what we need in this case. And look at the sections, which is polypropylene as well. And maybe the instance of E class is not really required. So these are the things that we need, and then we click apply. Yes to all. Okay. But if you look at what we have here, so polypropylene, the properties are already given because I've set this up before. So the elastic properties of polypropylene is 1.308 gigapascal with a Poisson ratio of 0.44, and the plasticity, which is the yield strength, is 40 megapascal at the plastic strain of 0. So that's really what you need, and then of course we create a section. So if we then go back to the porous media that we created before, so I can then do a section assignment. So by selecting this section, I'm ticking that and click OK. So now I want to make it polypropylene, and polypropylene is fine. So we can then try and mesh this model. So it's recommending 2, but probably let me use something a little bit, maybe small, something like 0.5, and then see what we get. So that looks too fine. So let's do 1. Okay, 1 is probably about right, so we have a fairly okay model. And then the other thing is that we want to use a triangle. Triangle is easier for this kind of porous media to use in our meshing, and then we can go ahead and mesh the domain. So that's the domain meshed. So there are a few other things we need to do. So I'm going to create some corner nodes because I'm thinking ahead of how I'm going to analyze and get stress strain data from this. So basically I'm going to hold shift and select all these other points and click done. So this creates the corner nodes, and then we can then work our way through the system. So we've got our materials, polypropylene, and then we've got the assembly. In the assembly module, everything is fine. So we can create a step. So I'm going to just use a loading step for this analysis. And static general is normally okay for a start for now. So we also need to ask for a certain history output that we need. So if we click on this, so I'm going to call it my corner node history output. So this is what we are going to use post-processing the job. And we link it to the corner nodes. And basically, I'm going to ask for RF1, RF2, U, coordinate 1, coordinate 2, U1, and U2. Basically, what this is the reaction force in the X and Y direction, the coordinate positions of those corner nodes. So their position in space, basically, in X and Y direction, and their displacement in X and Y direction. Those two are not necessarily the same. So the coordinate is basically the Cartesian coordinate positioning, and this is actually the displacement with respect to a fixed point in the system. So we're going to track all that and use them to extract stress strain data in the system. So we'll basically have that first, and then we can go look at boundary condition. So I'm going to do a tensile test simulation on this. So my X back would have to be a roller support, So remember, we're going to use periodic boundary condition. So the method of the periodic boundary condition I'm going to use only allows you to apply boundary conditions on the corner node, on the corner nodes. The spaces in between will be implemented with periodic boundary condition, using a software that again I've developed. So this is in the one direction. So we'll do the same and say, okay, Y base with the roller support. So we can go ahead and select that point and that point, okay? And that gives us loading in the Y direction. So remember, the spaces in between, we're going to leave them because that's what we're going to use for applying periodic boundary condition. Then the last bit is just to apply a load, what loading we want on this model. So I'm going to call it my X tensile load. It's no more going to be an initial step, it will be a loading step. And we're going to apply it on this corner. So because that's where I'm going to apply my displacement. So that will be in the one direction. And I'm going to use, let's say, maybe a 10% load because it's got a total length edge of 100 microns. So 10% will be essentially 10. So if you notice here, that's the loading. So we've got everything set up as it's supposed to be in this model. Then we can just create the job. So the job will now be Porous Media simulation. Maybe I said, we'll just leave that. Okay, continue. And that is done. Now, the next thing we're going to do is to set this job to run and then apply periodic boundary condition. But this is where you now need to get hold of, again, a second software that applies periodic boundary condition on the domain. I mean, the reason is that there is no classic way of applying periodic boundary condition within ABAQUS using, the ABAQUS FE environment. You probably have to do it from a program, from using a plugin. And so again, I developed a different software that does this, which is called PBC Gen 2D. Again, if you look in the description section of this video, you'll find that particular link for getting hold of that software. So let's just look at what it looks like. So when you open it, you'll basically again see one single file, nothing else. There's a little README file that tells you a little bit around what the software is about. Then all I need to do with this essentially is I'll copy the link where that information exists. I know it's here, and then I go back to ABAQUS and make that my current working directory because that's where I'm going to then be working from now onwards. Okay, so that becomes my current working directory, and the job that I set up, which is PM simulation we talked about before, I'm going to then write this as an input. So if we then go back here, so it appears right here as an input in this environment because that's my current working directory now. And then I can then go ahead and apply periodic boundary condition on this input file. So what do we do? So we just run, right click and run that code, select what we want, and then it goes ahead. So already it's detected that we have about quite a lot of nodes, and then it plots this graph, and then it plots this graph, so of which one of them represents all the nodes in the model. But what is most important for us here is the second graph, which tells you all the corner nodes, identifying them in different colors based on where positioning. So for example, the X positive phase internal nodes is X pos int, and then the green one is the Y negative, so this is in the negative side, in the bottom side. At the back we've got the orange, and at the top we've got the dark blue. The color nodes are identified as green. So again, these things are done inside MATLAB, but as well as doing this thing, it's also updating the original input file with periodicity argument, periodicity boundary condition argument. So let's look at what it's done. So if we open up this, okay, so if we drag this in here, so you can see instantly the code is there. Just to show you, so at the foot end here, it's got this extra nodal set, and especially this equation, star equation. This is the classic way that it applies periodic boundary condition on the domain that we've looked at. If you're confused about this and you want to learn here, so I've made 2 videos that I think will be very helpful for you, especially talking about the theory of what you've done. So please look here in the card and visit that video that tells you a little bit around the theory of periodic boundary condition, especially how I'm showing you how to do it. So now, right in this environment within MATLAB, we could go ahead and call the ABAQUS executor, so ABAQUS, and the job name that we have, which is basically this, so I'm going to call it, is equal to PM simulation. So that's job name that we are calling, and I'm going to ask it to show me it, to run it interactively. So the idea is that I want to see what is going on, and I'm running ABAQUS right inside the MATLAB environment. Of course, here I made a video that shows you a little bit about this, which you can see right here. So it's basically running, and we're going to get our results in the end. Okay, so you can see the report at the end here is that, okay, the job has completed as usual, and there you can see the normal ABAQUS results file that you generate as usual. Everything is fine. Then what we really want to do is to visualize the data. So I'm going to call the ABAQUS viewer, which is basically an interface for visualizing the result. So we can call it right up in ABAQUS, in MATLAB, and then it will create that. So we can then open the database, which is the simulation. Okay, so if we look at the result, then that's exactly what we wanted. So we can then look at the simulation. So that becomes the result, and instantly you can see that there is a clear pathway around here where there is a bit of weakness due to the porosity of the system. But generally, we have the sort of result that we want. There are regions where you've got a dominance of the intense stress history, stress of about 40 megapascal right across the system. And then there are some regions that don't have very high load. But more importantly, if we exaggerate this a bit, then we can see, so if I just make this 1 point. So you can see the periodicity argument, so there's a bit of periodicity there. All the way around the model, you've got the expected periodicity. Of course, the next step here is can I actually visualize the stress strain data that is generated from this. And also try and get some effective properties associated with this so that we can quantify the effect of this porosity, especially at 20% on the behavior of the system. So if we then want to look at the stress strain data, so we've asked for a certain history output, so we go and look for the history output. So essentially the coordinate position that we requested before, so I'll press down shift and select all that, and then lift down shift again, and then press down control, select that on the system, and then go all the way to the end and press while pressing down shift and control, select all of that. So basically I've selected all the displacement data, the reaction force data, and the coordinate position data, and then we'll plot that. So that will give us the first indication of what's really going on in the model and how the interactions is happening. But we don't want to stop here, so we go to tools, we go to plugins, tools, Excel utilities. So we're going to ask it to extract the current XY data into an Excel file, so that we'll get the raw data and then we can manipulate those raw data. So that's basically what the raw data is. So I'm not going to worry about what exactly they represent. I'm just going to Control Alt to select and Control C to copy. So I've already formatted this particular Excel file, which again I'll put for you in the description section of this video for you to download. Okay, so when we paste it, we get this data, and then let's just look here. So our length is 100 and our width is 100. The height is 1 because it's a 2D system problem, and then we can then extract the Young's modulus. If you want to understand exactly what is going on here, I do refer you to again videos that I've made on periodic boundary condition on this channel, and it will explain what is going on here, or you just study this Excel file. The final thing is just a comparison of the information. So based on what we found, so the Young's modulus here is extracted for the porous media case, and the strength is also extracted for the porous media case. Now, in the original case, which was polypropylene, we know that the Young's modulus was 1.308 Pascal, and the yield stress was 40 megapascal. So including a 20% porosity on this system has damaged these effective properties to these sort of numbers. And that is quite big, because 20% porosity for something like polypropylene is quite a lot. So you won't normally accept that high level of porosity. So that's really what I want to share in this video, on how you can model this and the implication of having so much porosity on the effective properties of the system, especially when you have periodic boundary condition incorporated in them. If you want to learn more around periodic boundary condition, the theory of it, then that's something you can use. If you want to see how you can actually do what I've done, especially the periodic boundary condition in a manual way, again, this is a video that will be useful to you. Thanks for your interest in this channel, and I'll see you in the next video.